how likely is something going to precipitate in solution? How do we use, principles of equilibrium to then determine, if we have a saturated solution, an unsaturated solution, or an oversaturated solution. So usually when we want to compare which way a reaction goes, we use what? When we find out which direction a reaction moves, what do we use? What's a quantitative way if your reaction is going to go forward or backwards?
Your QC value against your...
Yeah, you compare the reaction quotient to determine the direction of the reaction itself, right? And the reaction quotient again was our variable Q, right? And all we do for the reaction quotient is just plug in our non-equilibrium values. So those are our initial concentrations of whatever it is that we're looking at. When we look at a reaction that is a solubility process, like let's say calcium CO3, this is calcium carbonate, which is our solid, and this goes to Ca2 plus, aqueous plus CO3, 2 minus, aqueous. When we look at the reaction quotient here, we're looking at, is this going to be in a solution that's oversaturated, undersaturated, at equilibrium, and that tells us whether or not we're going to precipitate this solid in our solution, right? So where's the I? That's where I put the dot, right? So if Q, SP, right, where SP just means the solubility product, we just call it the solubility product now instead of just the regular equilibrium constant, because when we write the equilibrium constant for this process, what are the only things that the equilibrium constant depends on?
Aqueous state?
Yeah, the aqueous state, right? So it's just a product between our two concentrations of the product side of the reaction, right? So it's not really a ratio anymore, it's just looking at the product of these two concentrations. And so if QSP was less than KSP, right, our equilibrium solubility, what kind of solution did we have? Unsaturated solution, right? This was an unsaturated solution. And we can write that, right, because if we look at KSP equals Ca2 plus CO3 2 minus, right? This is what our solubility product is actually equal to. If that value is less than those two, that means that the concentration of the aqueous ions in solution is lower than what we expect it to be, right? The product of these two things is smaller than what we expect it to be, so we need more of that in solution before we reach the equilibrium state, right? Which means that we can dissolve more still. That's all that's saying. We can dissolve more still, which means we have an unsaturated solution. We can still dissolve the salt in our water. If QSP was equal to KSP, what kind of solution did we have? We had a saturated solution, right? So that means that we're at the equilibrium. We basically put the maximum amount of our aqueous ions in solution that we can, right? Based off of our equilibrium constant. And at this point, what is the concentration, in this case, because the stoichiometry works out, of calcium and carbonate related to? What other quantity is that related to? That we talked about, not in exactly last lecture, but the one before. So when we're at the maximum amount that we can dissolve in solution, that means that the concentration of those ions is equal to it is related to the solubility product, right? But what other quantity related to solubility was related to the solubility product or the equilibrium constant? All right, we defined it when we made our potassium tartrate solution 2.5 weeks ago. Or 3 weeks ago now, maybe. The molar solubility, right? at this point, if it's a 1-to-1 ratio, Ca2 plus equals CO3 2 minus equals the molar solubility. Right, that equals the molar solubility, or the maximum amount that we can dissolve in whatever solution is, right? So this is gonna have units of moles per liter. It's the maximum amount of this we can have in solution. In that quantity, again, the reason that it's equal to these concentrations in these cases is because that's the amount of solid that we lose at equilibrium, right? And when you set up an ice table, the amount that we lose that is equal to some value x. And because it's a 1-to-1 molar ratio, that means whatever we lose in this, we get 1 mole of calcium, 1 mole of carbonate. That's why those two concentrations at equilibrium are equal to the molar solubility. If these had, coefficients here, then they wouldn't be exactly equal to, but they would be related to it in some way, like either to the molar solubility squared or whatever the coefficient was in that case. And then when we had a situation where QSP was greater than KSP, how do we define that solution? Supersaturated or oversaturated solution, right? This was a supersaturated solution. That means that our concentration of our ions at that initial state is too high, so we need less of it, and the only way that we get less of it is that we force this reaction to go in the opposite direction. Right, so this reaction is going to move in the opposite direction to make less of those ions, which means that we're going to precipitate our ions into that solid now at this point. Right, and then we looked at that, and if we compare, or what we'll look at today is that when we compare these different solubility products, we can then determine, okay, which ion or which solid is going to precipitate first based off of these solubility products. Right, so that's how we talked about the reaction quotient in relation to the solubility product last time, and then we came up with another thing that's going to be important for equilibrium in general. When we looked at setting up equilibrium tables for this, we looked at the common ion effect, right? And what did the common ion effect do?
There's a common ion in 2 different chemical.
Yeah, if we have some common ion for our reaction, so let's say we have calcium carbonate again, just because we already used that. This goes to Ca2 plus, a CO3 2 minus. These are both aqueous. And in solution, so before we dissolved calcium chloride, right? So that went to, this reaction really isn't going to go in both directions, but Ca2 plus aqueous plus 2Cl minus aqueous. If we were to dissolve some calcium in solution, then now when we look at the solubility of this other solid, right, this ion here is like adding more of this calcium concentration, which Avoir's principle says that shifts the reaction in which direction? To the left, right? So now because we have this common ion from this separate thing that we did beforehand, right? This is something that we did before we put in our calcium carbonate. The fact that we have this in solution already makes this solid less soluble, right? Because we already have some of this. And we showed that explicitly because if you set up an ice table, right? Now you're not starting off with 0 of both of your products here. You start off with whatever concentration of this you already have in solution, right? And you see when you solve for the molar solubility in that case for calcium carbonate, then you see that, okay, it's going to be a lot less soluble, right? Even a concentration of 1 molar for the chloride ion that we looked at last time was like something like 10,000 times less soluble in that solution. And then when we solved that problem, we used an approximation, which we called the small x approximation, right? And this was just a mathematical tool to kind of simplify the problem, right? Because when we start getting coefficients that are going to give us powers of x in our ice tables that are larger than 2, we don't really want to solve those, right? We don't have an exact form or a simple solution like we do for the quadratic formula. So what was the small x approximation? Does anyone remember? I can summarize it in a sentence. Colin?
Pretty much the x is so small that you can ignore it.
Yeah, so if KSP or K, the equilibrium constant in general, is very, very small, then we know the change on the way to equilibrium is going to be very, very small. So if we have something like 1 minus x, if 1 or x is much smaller than 1, then we can say that this is approximately equal to 1 in this case, right? So this will allow us to simplify terms in our polynomials, right? When we're solving for this change on the way to equilibrium. And this isn't just for our solubility product. We'll use this a lot for acids and bases because the equilibrium constant for an acid tends to be very, very small. And in general for equilibrium, right? We can just have a small value for the equilibrium constant, right? So we introduced the idea of this small x approximation, right? So we want to make sure that we're aware of that or thinking about that. And the same thing with everything as we're doing these ice tables, are the values that I'm getting making physical sense, right? When I end up with more than what we started with, we can't have negative values for concentrations. Small x is something that allows us to kind of stay on track, right? This is going to be a small concentration, or if I'm trying to solve something that has to the power of 7, right? Probably not on the right track there, right? I probably got to simplify the problem. That should tell you that, okay, I need to simplify this somehow because I don't actually have the tools to solve this right now. All right, so that's where we ended off with last time. So before we get started on today, we're going to talk about selective precipitation and talk a little bit about using equilibrium with complex ion formation, right? Which is going to be the opposite of solubility in the sense that complex ions usually have very, very large equilibrium constants because they're almost entirely going to form your complex ion. But before we do that, let's see if we can solve this equilibrium problem. So why don't you guys take 5 minutes or so and see if you can set up how to find the equilibrium concentrations of the two products in this case. And as always, I can come over and help you get started. If you're stuck, you just raise your hand. You can talk to your neighbor, socialize. so you wanna be able to at least set up the ice table, right? You get there, you're 80% of the way to finishing the problem. Let me put 0.0025 minus 2x. You would have to do a small x approximation here, yeah.
Okay, I was like.
Yeah, I thought about it after you said it. I hadn't considered it before, but you do have to do a small. Let me erase this before it pops up. I don't want to rob you guys the chance of getting the right ice table, so. Why is that? So for the quiz, for example, you're not gonna have to do any small x approximations or anything like that, but for, the exam and future quizzes, you might have to recognize that. Alright, so for our initial concentrations here, what do we have for all of them? What do we have for H2S, hydrogen sulfide?
0.0125 moles.
Yep, 0.0025 molar. For this, you can actually leave it in terms of moles if you want till the end, and you can then just divide by the liters at the very end if you want to just find the concentration of the other two as well. Both of them are work equivalently. If you want to work in concentrations from the beginning, you can. And then what about for hydrogen gas and sulfur gas? They should be 0 for each of those, right? Well, how do we know? Well, it initially only contains the hydrogen sulfide, right? So that means that for each of these, this should be 0 for both of them, right? Then on our way to equilibrium, how much of everything are we losing and what's the sign, right? How do we know which direction this reaction is going to move?
Towards the or products.
It should move towards the products, right? And we know that because, well, we don't have any products starting off here, right? So that indicates, okay, this reaction only has one direction it can move in. At this point, if we want to do this quantitatively, how would we do that?
Plus, we could put.
If we wanted to show which direction the reaction moves quantitatively, right? What tells us if it moves forward or if it moves in the reverse direction?
Oh,
The reaction quotient, right? Q, right? We can always look at Q if we're unsure which direction it's going to move in. So we look at how Q compares to Kc. What should Q be equal to here?
0.
0, right? Because Q is equal to products over reactants, which will be our initial concentrations of H2 squared S2 not squared over H2S squared. Right? What are our initial concentrations for H2 and S2? 0, right? So that means that Q is going to equal 0. So we have 0, and what's our value for Kc? (1.67 times 10 to the minus 10, right? This is a really small value, minus 7, sorry. This is a really small value, but how does it compare to 0? It's still larger than 0, it's just slightly larger than 0, right? So this is still larger which means QC is still less than KC. When QC is less than KC, that means that we need to make more products to get it to equal the equilibrium value. So that means that the reaction will shift to the right. And when that happens, that tells us the sign of the change on the way to equilibrium, right? The reaction is moving in this direction. Are we losing or gaining hydrogen sulfide? Losing, which means the sign for that change should be negative, right? Are we gaining or losing hydrogen gas? Gaining, so it should be, what should the change be, positive or negative? Positive, and then what about sulfur gas? Positive, right? So that tells us the sign of the change right here. And then what tells us the actual change, right? We're gonna label our change some arbitrary constant, and what tells us we have to multiply it by a coefficient or anything? The stoichiometry of the reaction, right? If we lose anything in this reaction moving forward, if we lose any hydrogen sulfide, every time we lose one reaction happening, we lose 2 molecules of this, right? So 1 mole of this reaction happening, we lose 2 mole of hydrogen sulfide. So that'd be minus 2x, where x is our arbitrary change. What about for hydrogen gas? How much are we gaining? Plus 2x. And then what about sulfur gas? Just x, right? Because it doesn't have a coefficient in front of it. So now we just add our initial and change to get our equilibrium values. So this is going to be 0.0025 minus 2x. This will just be 2x, and this is equal to x, right? So all we did is we put an imaginary line here, and we just add those 2 rows together. The initial and the change gives us our equilibrium values. And these equilibrium values, right, these we now plug into where? What do we do with these once we have these? Yeah, so we're gonna get some polynomial, right, solving, but where do we plug those into? An expression for what?
Oh, for K.
For our equilibrium constant, right? Our equilibrium constant gives us the ratio of products over reactants to their stoichiometric coefficient at equilibrium, right? And those are the concentrations that we just solved for, right? We don't know exactly what they are yet, but we know that they're related to the initial values by this relationship. So this gives us, if we plug everything in, 1.67 times 10 to the minus 7 is equal to, then we have 2x squared times x over 0.0025 minus 2x squared.
Was it 0.025 or 0.25?
It was 0. It depends if you're doing it in terms of moles or concentration. I already changed this to the concentration. This is 0.0125 divided by 5 liters, right?
So you
And
can
that-
do it there, or you can do it.
You can do it there or you can do it afterwards, right? If you do things in terms of moles, you're always going to end up with the right answer. If you have weird volumes changing and stuff, then sometimes it's easier just to work in moles. But in general, you can usually do it both ways. You just have to make sure you're working with the appropriate total volume, right? If you mix 2 things of different volumes, your initial concentrations are the moles of that in the total volume rather than the initial volume that you used when you mixed it. And in the one problem that we didn't do on the last lecture, actually, the last one has a situation like that. You mix 2 solutions of lead nitrate or lead 2 nitrate and sodium bromide, and or sodium chloride or something. And then those are 2 different volumes, and you have to make sure you get the appropriate total volume to do the problem after that. Right, and so now, what Noe mentioned before is, well, this gives us something that's going to be like a cubic equation, right? Because in the numerator, we're going to get 4x to the third over 0.0025 minus 2x squared, right? So this can be something pretty nasty to solve, right? We don't have tools to solve a cubic equation unless it's something very simple, like just taking the cube root of both sides. We can't do that because if we take the cube root of the denominator right now, we end up with 2 over 3, right? It doesn't really help us very much. So this tells us we're probably gonna have to make an approximation to simplify this problem. If we look at the value of Kc, what can we say about it? The size of it.
It's very small.
It's very small, which means this change, right? That means that the reactants are favored at equilibrium, right? So this change, when we only have initially hydrogen sulfide, as we move towards equilibrium, we're only going to make a little bit of this. Why? Because the equilibrium constant is very small. So that means that this change is going to be very small as well. And when we look at it comparing to a value like 2.5, that's something like 10 to the minus 3. And this change is probably going to be on the order of somewhere around 10 to the minus 4. Or not, sorry, 10 to the minus 4, 10 to the minus 7, right? So there'd be a 10 to the 4 difference between the two. It'd be about 1,000 times smaller. So we can use a small x approximation. And when we do that, how does this simplify the term in the denominator? How does this simplify that? So it isn't necessarily going to become 1. 1 was the example when I mentioned it here. The reason that this approximate equals 1 is because you're doing 1 minus something small is basically equal to whatever this was right here, right? This is 1 minus x is approximately equal to x, or sorry, 1, because this is what you're subtracting x from. Here, what are you subtracting x from? 0.0025, right? So the small x approximation is saying x is small compared to this number right here. So I'm going to say that this is approximately equal to just this number inside the parentheses here, right? This is small, which means 0.0025 is much greater than 2x. So this goes to 0.0025 squared. And I'm not going to put goes to, I'll put is approximately equal to. Right? And this isn't an issue now anymore to have this in the denominator. Because we can, even if it is, to the power is 2/3, that's just a number to that power. We can always just plug that in our calculator and get an answer for that. So that simplifies that a lot. So now we get 1.67 times 10 to the minus 7 equals 4x to the third over 0.0025 squared. Continue this on the next page. So all we have to do now is isolate x cubed, then take the cube root of both sides. Cube root of both sides only has 3 solutions, but this is going to be 0. Actually, this one's only going to have 1 solution. So this becomes 1.67 times 10 to the minus 7 times 0.0025 squared equals 4x cubed. All I did was I just multiplied 0.0025 to both sides. Divide both sides by 4. 1.67 times 10 to the minus 7. 2.5 times 10 to the minus 3 squared. I'm just writing that in scientific notation so it's easier for me to plug it into a calculator. x to the third. I can cube root both sides. And then that'll give me my answer. Which gives me 2.5, 1.67 times 2.5 times 10 to the minus 10, or 10 to the minus 12 over 4. Something like that, which will give me 1.67 to the 1/3, 2.5, 2/3, 4, 2/3 times 10 to the minus 4. You don't have to do all these. I'm just doing this so I don't have to plug it all in my calculator. Cube root times 2.5 x to the y divided by 4 to the cube root. Let me see if I did the algebra. I give out 1.37 times 10 to the minus 4 equals x. Oh wait, this is gonna be 6, not 5. 6 plus 7 should be 13. Oh man, this is gonna simplify a little bit differently. Times 10 x to the y parentheses 13 negative divided by 3. 1, 2, 3, 4, 5. $6.39 times 10 to the minus 1, 2, 3, 4, 5. All right, so the change is about 10 to the minus 5, or we said the small x, we're comparing it to about 10 to the minus 3, right? That's probably just on the edge where this is an appropriate approximation. All right, it's about 100 times smaller, so. So this is what we would get for x, which is equal to our hydrogen sulfide concentration. And then we would just multiply this by 2 to get our concentration for hydrogen gas, right? Because hydrogen gas was just equal to 2 times x, right? So x was equal to S2, and 2 times x was equal to the hydrogen concentration. Right, so this is a standard equilibrium problem. We just have to identify what we're starting off with, which direction the reaction moves, set up our ice table, keeping in mind stoichiometry to get our equilibrium concentrations, and then use those to then solve for the equilibrium concentration. In this case, we had to do an approximation to get this polynomial to simplify, because if we don't, then this becomes a cubic equation with 3 different roots, which is too hard for us to solve. So we use a small x approximation that allows us to then solve for x. All right. How did we feel at least up to this point right here on the ice table, setting up the ice table? Thumbs up, thumbs to the side, or thumbs down. All right, so if you're at least comfortable with up to this part, that's a good spot to be in, right? Because this is, 80% of the problem. Everything after this is just math, right? All of the chemistry is involved in setting up this right here. This is the chemistry knowledge. After that, this is just math at that point, right? We're just doing algebra. So try not to get lost in all this, especially with the small x approximation. This is 80% of the way there. Can we set up this table, right? All we're looking for is what we start off with on the way to equilibrium, right? Because they're starting out at equilibrium. How do we get there? These are the concentrations at equilibrium that then we put into our equilibrium constant, right? This is the same relationship that we're going to be using all month, right? Equilibrium constant, doesn't matter if it's solubility, gases, aqueous reactions, acids and bases, complex ions, that's the same relationship for all of them, right? Products over reactants at equilibrium. Okay, all right, so I just wanted to start off today going over one of these. It'll probably be a good idea just to kind of go over them as we are going through. I guess I skipped a, wait, did I skip a slide on accident? Okay, yeah, so that's where the first slide was. Just going over an ice table problem, right? It's good because you guys are gonna be doing a million of these. So the more we see it, the more we're comfortable with it, the more we kind of sit with ourselves and like really test ourselves, can I get through at least setting up the equilibrium constant? Perla?
We have to solve for the 2H2.
We can solve for 2H2, right? So this H2 is just equal to 2 times X, which is equal to, it'll be 12.6 or 78 times 10 to the minus 5. All right, I just multiplied this value by 2 to get that value. And you could simplify this scientific notation too. So it'd be 1.2 or 1.3 times 10 to the minus 4. So that's all we have to do. Once you get X, then you're 99% of the way there, right? If you have X, even if they both have different stoichiometries, you're just multiplying this or subtracting this from a number. Multiplying it to a number or subtracting it from another number. Right, and if we wanted to solve H2S, right, how would we solve for the concentration of H2S? Right, the question didn't ask for that, but how would we solve for that?
You would just use them as equilibrium constants to isolate for H2S and set it equal to 1.67 times 10 to the 7.
So when we solve for X, we did set up that's exactly what we did, right? We used the equilibrium constant and then solve for this value of X. Once we have X,
you just subtracted by.
yeah, we just plug it into our relationship for this right here if we wanted to solve for H2S. Right, so if we did this, we would just do 0.0025 minus 2 times 6.39 times 10 to the minus 5. And then once you plug that in, then you would get the answer for that. And let's see if it's the small x approximation was decent. If it was 0.0025 minus 2 times 6.39 times 10 to the 5 minus, we would get 0.0024 if we're rounding it, right? So small x approximation is probably okay there, right? We see that this number hardly changed at all on the way to equilibrium, right? So intuition about how things are changing or how we expect them should help us gauge whether this answer is right or not. Okay. All right, any other questions on this problem? Or is anyone still looking at this? No? All right, so let's take just a little bit of time to talk about selective precipitation and complex ion formation, and then we'll take a break, and we'll come back, and then we'll take the quiz, right? So the technique of selective precipitation is just a technique of separating 2 or more ions in solution by adding a reagent that precipitates one before it precipitates the other, right? So this is selective precipitation. So if we have some mixture of ions like this solution right here, and it contains a certain concentration of barium and strontium, and to the solution we add potassium chromate, right? The potassium chromate is going to act as a source of Cr4 2 minus ions, right? And what this does is that both of these ions can form precipitates with the barium and the strontium. And sorry, I know the slides are a little mixed up right now. And so what we have to ask ourselves is both cations will form precipitates, or PPT is what we use, with the chromate ion. And based off the KSP values, we can determine which one is going to precipitate first, right? So if we have a smaller KSP, right, so we have that for barium chromate, compared to strontium chromate, which one do you guys think is going to precipitate first? All right, which one do you think is going to be more or less soluble, right? Think about our thing is like we have a solid that goes to aqueous ion plus aqueous ion. Based off of the value of KSP, that tells us which one is going to be more soluble in solution.
The SR is gonna be what? I think
The SR should be more or less soluble either.
it's more soluble.
It's more soluble because this is a larger value than the barium chromate, right? If it's a larger value, that means that we have more aqueous ions at equilibrium. Why? Because KSP is equal to concentration of in this case, SR 2 plus, CrO4 2 minus. KSP here is equal to barium 2 plus, CrO4 2 minus, right? This means that the concentration of these at equilibrium is larger than the concentration of these at equilibrium. If we have more of these, right, and each of these are the aqueous ions, right? These are the ones that are in the aqueous phase. So if I have more aqueous stuff for strontium, that means that I have more ions in solution. That means this is going to be more soluble. It's going to allow more ions to form in solution. Whereas this one, we have less ions in solution, so this is going to precipitate first. Right? This one has less ions in solution, so this solid is less soluble in the solution, and it should precipitate first. So that means that we need less chromate to precipitate the barium than we do for strontium. Right? We need more chromate for this. So this is going to be less soluble, and this is more soluble, right? Because the equilibrium constant for strontium chromate is larger than that for barium chromate, which means that there's more aqueous ions for strontium chromate at equilibrium than there is for barium chromate at equilibrium. And so what that means is that if we're adding chromate to the solution, we should then be able to determine, well, how much do I need to add to precipitate this? And by the time I've, added enough to start precipitating this, how much of that should be left? Right, we're kind of thinking about the equilibrium as kind of the tipping point here now, right? If we're at the equilibrium values, that means that we're starting to make solid of, right, we're starting to precipitate crashes out of solution. And then at the equilibrium point, that's when we know we have the maximum amount of barium ions in solution before it starts to precipitate, right? Another way of saying that in terms of the solution would be what? What kind of solution would that be at equilibrium? Right, when we first talked about the QSP and KSP, comparing those today, right? Which one does that fall into? If QSP is less than KSP, equal to KSP, or greater than KSP. If you're at equilibrium, what's the relationship between them? Or how do we define that solution when QSP equals KSP? There's no movement, right? And when there's no movement, that means we've reached what state? equilibrium. And when we're at equilibrium, that means that we've dissolved the maximum amount in solution, right? So any more that we add is going to start precipitating the solid. And so if we're looking at a problem, like how we can ask this, these are usually phrased in a form like this. So the magnesium and calcium ions present in salt water can be precipitated out by adding potassium hydroxide to precipitate the insoluble hydroxide. Hydroxides are going to be the next metal cation we look at in qualitative analysis, right? And so if you know the concentration of both of these ions in salt water, which are given here, and you know the equilibrium constant, because someone spent their life determining these constants, for these insoluble hydroxides, you should be able to determine which one is going to precipitate first, right? So in this case, which ion should precipitate first?
The magnesium,
Yeah, so what tells you that the magnesium will precipitate first?
because it's much smaller, so it'll take a lot less QSP. Like QSP has to be, doesn't have to be as large.
Exactly right. It's because the equilibrium constant is very, very small, right? 10 to the minus 13, much smaller than 10 to the minus 6. That means this compound is less soluble than calcium hydroxide. Meaning at equilibrium, we have much less magnesium and hydroxide ions in solution than we do for the calcium magnesium. So then this tells us that magnesium hydroxide, the KSP for magnesium hydroxide, is much smaller than KSP for calcium hydroxide. So it is less soluble in solution and will precipitate first. So what we're doing here is we're just comparing the values of KSP to determine this. To determine which one is going to precipitate first, right? Because KSP tells us, well, how many aqueous ions are we going to have in solution at equilibrium? Any questions on why the lower or the smaller KSP determines which one will precipitate first? All right, and so then another way that this will be phrased commonly is, well, what's the minimum amount of hydroxide that's required for the first ion to precipitate? Right, so there's some key words to focus on here. What's the minimum amount of OH concentration, right, hydroxide concentration, required for the first ion to precipitate? And so the first ion was magnesium 2+, right? That's the one that we want to precipitate. So how much OH minus do we need? So does anyone have an idea of how you might find the minimum amount of OH minus to precipitate?
Is this based off the molarity values on the other one? Or yeah, on part A.
Yeah, so now we have some initial concentrations, right? Or not some, yeah, we have some initial concentrations, right? We have this concentration in solution. And we want to find out how much of added KOH do we need to precipitate the solution? And what's the minimum amount we need, right? So when do we go from aqueous to precipitating things? At what point do we switch from that, the aqueous phase, to starting to crash stuff out of solution?
When Q is greater than KSP.
When Q is greater than KSP, so the turning point would be what? Right, we don't have values for Q necessarily, right, because we don't have any value for KOH, right? What's the turning point between a saturated solution and an unsaturated solution? Or an unsaturated solution and a saturated solution, depending on which way you're looking at it. Sorry, a oversaturated solution and an unsaturated solution. What's the special point in between those? the saturated solution, right? So I accidentally said it first, so that was the hint that was the answer. But the saturated solution, right, which is when you're at equilibrium, is the point at which you tip from aqueous to precipitation, right? Once you reach equilibrium, then you're right, you're happy, your happy state, right? You're not going to precipitate stuff out of the solution. You have the maximum amount dissolved in that solution, right? So the minimum amount of OH required is how much OH minus is needed to reach equilibrium, right? And how do we know how much OH minus is needed at equilibrium, right? If we're given the solubility product, that tells us for a given amount of magnesium how much OH minus is needed, right? So this is asking how much OH minus is needed for our concentration of magnesium, which we know is going to precipitate first, 0.059 molar magnesium 2 plus to reach equilibrium. Right, so whenever the question is asking what's the minimum amount, or sometimes they'll ask in another way, what's the maximum amount of this we can add? What's the minimum amount that's required for the first ion to precipitate? That's saying how much OH minus do I need to reach equilibrium? And if you're given KSP and the amount magnesium, then all you have to do is solve for OH minus. So how would I set up an equation to solve for OH minus here?
KSP equals concentration of magnesium times concentration of OH.
Right, this is our equilibrium condition, right? Magnesium 2 plus, OH minus, like that. This is our condition at equilibrium, right? This is only true at equilibrium, which is what the question is asking for. At this point, we're looking for this point right here, right? This is the condition at equilibrium. Except, I'm missing one thing here. All right, if I look at the precipitation reaction for MgOH2, right, this is my solid. I get Mg2 plus, and how many OH minuses do I get from that dissolution? I get 2, right? So I get plus 2 OH minus, and these are both aqueous. So this just needs to be squared because we have a 2 there. And so I know my value for magnesium because that's given to me, that's the concentration in salt water. And I know my KSP, so I just solve for OH minus. So I get Mg2 plus, Mg2 plus. This cancels out on that side. We get KSP over Mg2 plus equals OH minus squared. I raise everything to the 1/2 power. So just square root both sides. And then that's going to give me my answer. That'll give me my concentration. And so Daphne brought up a good question in office hours on Tuesday. She said, well, usually when we look at gases and aqueous stuff, if we have 0 on one side of the reaction, that means that we're going to shift in that direction, right? So if I'm just starting off with magnesium in solution and 0 of magnesium hydroxide, how come the reaction just doesn't move to the solid right away? So there's 2 different ways that we can look at this. The way that's kind of basic equilibrium is we know that what states of matter don't affect the equilibrium at all. Solids don't affect the equilibrium, right? So the presence of the solid or no solid doesn't tell us which direction the reaction is going to move. Why? Because if it's there or if it's not there, it doesn't shift the equilibrium. The only thing that matters is the concentration of the ions in solution. The other way we can interpret it is if we look at this and say, well, I need some critical amount to start precipitating stuff. How much of that do I need? Well, I need equilibrium concentrations at least, right? Because I know once I get to equilibrium, I'm saturated. Anything more I add is going to crash out the solution. Basically, if I don't, even though I don't have any of this on this side of the reaction, I need to reach some level of these concentrations before that even starts to crash out a solution. So if I have 0 of this, I still have, an equilibrium constant that is much smaller than the KSP. So that's why we don't just shift to making the solid right away. 1, because solids don't affect the position of the equilibrium, and 2, because I need some critical concentration of those before I start to precipitate. All right, and so continuing with the problem, then we get, what was the values? It was 2.06 times 10 to the minus 13, 2.06 times 10 to the minus 13 over 0.059 to the 1/2 is equal to my OH minus concentration. So if I plug that in, 6.0 or 2.09, 06 times 10 to the 13 minus divided by 0.059, enter square root. I get 1, 2, 3, 4, 5, 6, 1.9 times 10 to the minus 7 molar. Right, this is the critical amount of hydroxide I need to add, right? So very, very little to this solution because I have so many magnesium ions in solution to then get it to start precipitating. Any more hydroxide I add is gonna then shift the equilibrium and start precipitating out my hydroxide ion. All right, so this problem, in terms of the math for this problem, isn't that conceptually isn't that difficult, but the ideas behind it, setting up what it's actually asking, is the hard part for this problem, right? We need to kind of decipher the minimum OH. What does that mean? That means that we need the equilibrium concentration for OH such that this is true, right? Because at that point we have a saturated solution. Any more is going to precipitate that ion or this ionic compound out of solution. And so then you can ask, well, when the calcium starts to precipitate, right, which is our CaOH2, this is our other reaction, calcium 2 plus, and 2OH minus. When this starts to precipitate, what is the magnesium concentration that's left in solution? Right, and so when we ask, when does the calcium begin to precipitate, what is that asking?
What the minimum value of like OH is for that part?
Yeah, what is the minimum concentration of OH minus, that we need now to precipitate calcium, right? This is just saying the same as part B, but for calcium 2 plus. Right, so we can do the exact same thing. We're gonna have the KSB for calcium 2 plus, bless you, divided by the OH, the calcium concentration is equal to the square root is equal to OH minus, right? Because the stoichiometry is gonna be the same for this, it's gonna give us the exact same relationship. We're just gonna have to plug in different values for that. And I believe that value was 4.68 times 10 to the minus 6 over, I don't know why I didn't look at this one, 0.011 1 molar to the 1/2 equals, so I'm plugging it into my calculator, that should give us 2.06 times 10 to the minus 2 molarity, right? So again, this is about 10,000 times more calcium we need to precipitate, hydroxide. 10,000 times more hydroxide to precipitate the calcium than we needed for the magnesium. Why is that? Just because the calcium hydroxide is so much more soluble in water. So this is our OH minus concentration, right? And the second part of this question is saying, well, what is the magnesium concentration at this point?
You just plug it back into the first one.
Yeah, that's exactly right. This is saying what is the equilibrium magnesium concentration at this new OH minus concentration, right? So that means that we're trying to solve for the magnesium concentration given the hydroxide concentration that we just solved for, except, and what is the equilibrium at this new concentration?
Would it be the old one?
Hmm? Right, what is the equilibrium concentration of magnesium when we've added this much hydroxide now? So to do that, we have our KSP for magnesium, the solubility of that is equal to Mg 2 plus concentration OH minus. Now we've added so much OH minus that the equilibrium has shifted, right? But we know what the equilibrium concentration of this is here because we just solved for how much we've actually added to solution. So all we have to do is divide both sides by OH minus squared. We get KSP magnesium over OH minus squared. That's, what was that value? It was 2.06 times 10, is it 10 to the minus 3? There's no way that was it. 1.2 times 10 to the minus 10. 1.2 times 10 to the minus 10 over 2.06 times 10 to the minus 2 squared will give me the magnesium concentration. All right, so I took this value, that goes in the denominator here because that's our amount of hydroxide that we've added to the solution, and we get 4.9 times 10 to the minus 10. 4.9 times 10 to the minus 10.
Wait, I think you're using the one for BA for the 1.2 times 10 to the minus 10.
Oh, that was the one for BA?
Yeah.
Da, 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 da. Oh, I see what you're saying. Yeah, so it should be 2.06 times 10 to the minus 13, right? Sorry, that was the previous. 2.06 times 10 to the minus 13. And so if you went and you calculated the percentage of what you started with, which is 0.025, and now you have something like 10 to the minus 10, right? You would see that by the time you start precipitating out the calcium, which is when the hydroxide concentration is this much, you've already gotten rid of 99.99999% of the magnesium ions in solution. So by the time you even start precipitating the calcium, you've already gotten rid of almost all of the magnesium from solution. So when we're doing selective precipitation, if you have two different ionic solids that have large enough differences in their solubility product, you can selectively precipitate them just by adding whatever it is that creates the ionic compound, whatever counterion you need for that, and then naturally you filter one out because one is going to precipitate a lot easier than the other one. All right, any questions on this, right? So this is asking the same question, it's just in a different way, right? It's saying when calcium starts to precipitate, right? That means at the point at which calcium now starts to precipitate is when you reach equilibrium with the concentration of calcium you have in solution, right? We need to find out how much hydroxide we need to do that. How much magnesium is left is saying, well, given this amount of hydroxide ion in solution and our equilibrium relationship for magnesium, what's left over of the magnesium. Right, so the question really only has, a maximum like 10 words in that question, but how much, understanding the sequence of events that lead to your final answer here is somewhat more complicated than what it would seem from the question. All right, any questions on that? All right.
I guess just for like clarity, would the answer change also? Because I think that's for the
For which one?
like where it says 4.9. Would that
Oh, no, I already had it calculated. I didn't plug it into my calculator this time. I just looked at it. Sometimes I'll plug it into my calculator to slow myself down a little bit, but I'm running out of time, so I just had the value already ready. That one should be the correct answer. Yeah, that should be the correct answer. I think what threw me off is just the fact that these are both 2.6. So then when I looked at the previous page, I was like, well, I thought I was looking at the same value. All right, so we'll probably use just a tiny bit of lab to talk a little bit about complex ion equilibria, just because it's kind of cool and it's related to some of what we'll talk about at the end of the semester as well. But let's take like a 10-minute, 11-minute break, and we come back. I'll give you guys your second quiz, and then we'll move on to finishing up the first qualitative analysis.